So good morning. I would like to thank Professor Adhikari and Professor Ramana for giving me opportunity to talk here. So I'll talk some combinatorial properties of Apery-like number. So namely the property called supercongruence. So I'll define what is meant by Apery-like number and talk about the supercongruence. Okay. So let me start with Apery. He proved in 1970 in Johnny arithmetic. He proved that zeta 3 is irrational. So we know that the values of zeta as even integers are some rational multiple of pi. So this is transcendental, but we didn't have any idea of the Riemann zeta values at the odd integers. And Apery proved in 1978 in Johnny arithmetic that zeta 3 irrationals, and he defined two sequence of integers. So let me define this. So he used the sequence and choose k square n plus choose k square, k from 0 to n. He used this sequence of numbers defined by this binomial sums to prove this zeta 3 rationals. Basically, and he proved another sequence of similar type of numbers, and he used this number to show this rational approximation of zeta 3, and the convergence is so fast that he could prove that zeta 3 irrationals. So for example, these numbers, if you start with A0, let me give some example of the values, some values. So A0, I start with 1, A1 is 5, A2 is 73, A3 is 1445, A4 is 33001, and A5 is quite big. I will write here is 819005, and A6 is grow very fast, 21460825. So you see the numbers grow very, very fast. Also, he used in the same paper, he defined another sequence of numbers and choose k square, n plus k, choose k, not the squares. And he used this sequence to prove that zeta 2 is irrational. Already you know zeta 2 is transcendental, but he gave a proof that rational approximation of zeta 2 using this binomial, using these numbers bn's. And we can write some values of bn's. Similarly, this also grows very fast, something like b01, b1 is 3, b2 is 19, b3 is 147, dot, dot. Okay? So after this proof of Apery, zeta 3 rational, many people were interested to know properties of these ANs, namely combinatorial property or congruence property of these ANs and BNs. So, for example, the Chawla, Cowles, and Cowles, they proved that if P in 1980, they proved that the values of A, sequence A, is congruent to this 5 or A1, 5 mod P square, okay, for primes P bigger than or equal to 5. So that's in 1980, and the conjecture, in the same paper, Chawla, the conjecture that this is true for mod PQ for the prime P bigger than 5. And the conjecture was proved 2 years later by Gesell in 1982. And he proved something more general, that ANP is congruent to AN modulo PQ for P bigger than 5, and this is true for any n. So in particular, n equal to 1, this gives AP congruent to A1 modulo PQ. So this was proved 2 years later. Okay, so this is another type of congruence proved by Mimura in 1983. So all these papers appears in JNT. They prove that AP minus 1 is congruent to 1 modulo PQ for primes P is prime bigger than 5. So this is different type of congruence, and this is P minus 1, values at the point P minus 1, P is a prime number. So after this proof of this Apery, Bakers was interested how these numbers works, and he want to have a actually the numbers, the proof of Apery, it was kind of sometimes people are not convinced that how it is working. So, and people say that he was very lucky to get these numbers, and because the same thing does not work for others zeta values. So then Fred Bakers, he works, he tried to give a systematic proof of these numbers, and he was able to prove this zeta 3 irrationals using the theory of modular forms. So he went to study in a more systematic way, and he proved in 1985, again in JNT, he proved that for something more general congruence, for MR natural numbers, P bigger than 5 primes, okay, he proved that AMPR minus 1 is congruent to AMPR minus 1 mod P to the 3R for primes. And similarly, he proved also this same congruence for the number B minus 1 mod P to the 3R. So more or less, he generalized this congruence of Mimura for ANs and BUNs to a large number of, for any MNR. And this method of proof was a brute force use of combinatorics. There is no, this kind of use of very nice brute force argument with related to the binomial sums. And Koester, he wrote his PhD thesis with Bakers. In his thesis, he developed very systematic way of these congruences, and he proved that for any primes bigger than 5, he proved the similar congruence for the one we have discussing earlier for modulo P to the power 3R. Similarly, for the congruence B minus 1 modulo P to the power 3R. So the major part of his thesis developed a systematic way of proving this kind of congruence. If time permits, we'll prove a theorem according to method of Koester's. So this thesis is nicely developed how to prove congruence of this type. Okay, so this we call the supercongruence, means this is a congruence which seems to be easily proved, which seems to be 2p, but something 2 for the higher power of the p, like p cube. Okay, so it's the more than a congruence. It's something, it's not modulo p, but some higher powers. So that's why you say supercongruence. There is another type of supercongruence. Let me just write it down. So it's called modular. In 1985 again, he proved another kind of congruence. He proved that A at the value P1 minus 2 is congruent to the pth Fourier coefficients of a modular forms for prime P bigger than 5, and these ANs are Fourier coefficients of these modular forms eta 4, eta 4z. I define this to be the coefficients of A and Qn, where An is the nth Fourier coefficients of these particular forms. Here the eta z is the Dedekind eta functions, and we define this to be 1 by Q24, 1 minus Qn, and from 1 to infinity. And here this Q is E 2 pi I z in the upper half plane. So this is a, I'll not define modular form. This is a modular forms of weight 4. And basically you prove that the Apery number, the first one, at P minus 1 by 2 is congruent to the pth Fourier coefficients of these particular forms that relates these binomial sums, these combinatorial sums into the world of modular forms. And in the same paper, the conjecture, Baker's made conjecture that this is true for modulo p square. The same congruence is true for modulo p square, and it was proved by Algren and Ono in 2000 in a very nice paper using this Gaussian approximatic series over finite field. They use a kind of technique. This is proved by Algren and Ono in 2000. Okay, so similarly, the similar modular congruence is also true. This is proved by Algren in 2000 that P minus 1 by 2 is congruent to a pth Fourier coefficients of a modular forms. And here this BP means we take this particular modular forms and we take this nth coefficients. And this is a modular form in S3 gamma 04. Namely, this is a cost form of weight 3 and level 4. Okay, so this kind of congruence we call modular congruence because these numbers are related to Fourier coefficient of some modular forms. Okay, so let me tell you how interesting these numbers, and there are other numbers similar to these kind of properties that was studied by Beukos and Jagier. Okay, so let me come to Bn first, then I'll go to Ans. So Bns is recurrence relations. Okay, so Bn satisfies the relations, namely n plus 1 square Bn plus 1 equal to 11n square plus 11n plus 3 times Bn plus n square times B minus 1 for n bigger than 1. So this was shown by again Apery in his paper. And if you take this generating functions, namely summation Bn xn, this satisfies some differential equations, but I'm not going to the differential equations, just we are looking for the recurrence relations. Okay, or in general, one can consider, one considers, the relations bn plus 1 square b times first un plus 1 plus an square plus an plus lambda un plus n square times un minus 1 equal to 0. Something, okay, here these a, b and lambda are some rational parameters. Yeah. So, and then one say that we give this conditions u0 equal to 1, and you say that for which uns, okay, are rationals. Okay. So we are trying to generalize these numbers bn coming from the recurrence relations. So bn is a particular case of these recurrence relations. So now we are because ask the questions which values of a, b, and lambda gives you the solution un in integers. So okay, every time one needs to divide by n plus 1 square. Yes, and we want still that to be integers. Okay, so the question is which values of lambda the Bakers considers. Okay, the questions who is the values of a, b, and lambda yields a solutions in un in z. All the values should be in z. Okay. Okay, and a particular case is because now it is Apery numbers bn's. So Zagier in 90s he made a experiment with lot of data. So he found some. He said that if among these 1,000 millions a, b, lambda, he only found 36 tuples of a, b, lambda, which gives rational integer solution to these recurrence relations. And then he described those data, and Zagier in 2000, he found 36 tuples of a, b, lambda. Out of, he says that 100 million of this triple, and he found 6 special solutions which are sums of similar to binomial sums. Okay, so let me write those terms, namely an. So he gives 6 are special. 6 examples are. 6 are special. Special in the sense that they have nice representation like these numbers. So I'm writing these 6 numbers, these 6 sums, n k cube, k from 0 to n. Then the number bn, this is looks k from 0 to n, this interior part of 3 minus 1k, 3 to the power n minus 3k, and choose 3k, 3k choose k, 2k choose k, and number cn is looks like this is simpler, and choose k square, 2k choose k, and one number is this is his symbols dn, and this is exactly the Apery number bn. That's what I wrote in the second case, namely this k and choose k square and plus k choose k, and there are 2 more. Vn, this looks k is 4 to the power n minus 2k, and 2k, and 2k choose k square, 2k choose k square, and another sequence of numbers k, and this is double sums k and l, minus 1 to the power k, 8 to the power n minus k, and choose k, choose l cube. So the 6 and the values of a, b, lambda, one can write it down on the side. So he found these 6 binomial coefficients, and one of the case the Baker's numbers bn, okay, and then he analyzed something more. Also, he started studying this rational approximation using these numbers. But he said that the convergence is not very fast to prove anything on the limit. So in that sense, the bn's or the an's what Apery found were more special. Okay, so but as I told you, you are interested on the supercongruence of these numbers. So this number, namely, I'm interested on this kind of congruence. U MPR is congruent to U MPR minus 1 modulo p to the power kr, like the numbers proved by Coasters. BMPR is congruent to BMPR minus 1 modulo p to the power 3r. So using Coasters' idea or his proof, one can prove that the similar congruence is true for p to the power 3r. So this just come from the Coaster work, and then we could find that with Robert Osborne in 2011, we could not prove, it's still open. This congruence is true for p to the power 2r. So they come from the same recurrence relations, but this congruence is true for p to the power 3r, but similar congruence for bn's is true for modulo p to the power 2r. So, and this particular sequence Cn, we could able to prove that this is true for modulo p to the power 2r, again using in 2011 using the method of Coasters. And this is the usual already proved by Coaster. So Bn, and using the similar method of Coasters, we prove this that this congruence is true for modulo p to the power this 2r. Again, we prove in 11 that this congruence, this particular En satisfies this particular congruence modulo p to the power kr for k equal to 2. And there is still this is open, this is not yet proof, and we numerically check that this is true for p to the power r. So the mystery thing is that sometimes it's happening for 2r, sometimes it's happening for 3r, so we don't have any kind of thing where it's happening for modulo 2r and modulo 3r. The origin is the same, coming from the same recurrence relations, but still properties are different. Okay, so if time permits, I'll give a sketch of the proof using Coaster method of this particular congruence, which looks to be easy, yeah, compared to other case. Yeah, okay. So this is the story about Bn. So let me go now to the Ans. Okay, so the ANs satisfies, AN means the number I wrote in the beginning, satisfy this particular recurrence relations 2n plus 1, 17n square plus 17n 5an minus nq times an minus 1, and we start with a0 equal to 1 and a1 equal to 5. So this an satisfy, earlier it was the first term was n plus 1 whole squared n plus 1, but it's n plus 1 cube. So this satisfy the generating function of this satisfy third order differential equations. So there is a similar study of this number by Almqvist, then Van Straten and Judelin in 2011. They consider this general, consider these equations n plus 1 q a un plus 1 2n plus 1 times an square plus an plus b un minus cnq un minus 1. And they also ask the same question like Beukers or Jagias, which value of this a, b, c, the parameter a, b, c, a, b, and c, this gives a solution in the integers. And they got some interesting, it's not the complete answer, but they got some by doing this computer experiment. Let me write down. Yeah. A0 equal to 1, A1 equal to 5. The same thing. Yeah. And they got 6 interesting cases. I'm writing those numbers again. So the first one is, and got the 6 example, interesting example they found from here, namely n plus k choose k square. That's one example. That's the original Apery ANs, and choose k square 2k choose n square, and the number of the type n choose k square 2k choose k 2n minus k n minus k, and this let me see, let's tell about this numbers. Okay, from 0 to n minus 1 choose one type k, 3 times n minus 3k, n plus k choose k 3k factorial k factorial cube, and let me write another sequence, minus 1 choose k, k, and choose k cube, and this is something 2 plus 4n minus 5k 3n, and the last sequence is a double sequence, double sums, n k choose square, nl, kl, k plus l, n for certain values of a, b, c, and then the similar congruence we are looking, UMPR congruent to UMPR minus 1 modulo P to the power KR. So this was true for P to the power 3 var proved by Costas, and we could able to prove that here this is also true for P to the power 3R by Osborne, me, and Stroff or Minstoff in 2016, that this kind of congruence is true for this particular sequence modulo P to the power 3R. Again, you use not exactly Coaster method, but something more different. And yeah, same thing with this. We could generalize these two together and prove the same congruence here. And I like to mention that the congruences, the UMPR congruent to UMPR minus 1 modulo P to the power KR is open. We checked this is true for 3R, but we couldn't able to prove using Coaster method. This man used some method. And I think 2 years before, for R equal to 1, only, proved by, let me write, De Beiram and Tauraso. They proved for R equal to 1 only, this particular congruently, UP congruent to U1 modulo P cube for R equal to 1, that particular case. And this general case is not still yet known. Similarly, this satisfies the congruence P to the power 3R, and also this Osborne, Straub, and myself proved in 2016. And I'd like to mention that the similar congruence for this is open, and we could able to, we checked that this congruence seems to be 3R. So this is still, we have not understood well that they come from the same way of differential equations, but something is true in some case, other case, so they don't follow universal things. So there is no general phenomena works here. Still it is mysterious. Okay. So there is another generalization to these recurrence relations, and mostly they use in the series of 1 by pi or 1 by pi square. So Sean Cooper, he was trying to find this generalization of this Ramanujan type series for 1 by pi, and he showed that some numbers that come similarly from the recurrence relations, and that one can use to find this Ramanujan type series for 1 by pi. So Cooper in 2012, he considered these integral solutions to this more general recurrence relations equal to 2n plus 1 and an square plus an plus b un minus n into cn square plus b and un minus 1. So this is more general. There is one more a, b, c, d parameter here with the same initial condition, a0 equal to 1 and a1 equal to 5. He tried to find this something more. If you put d equal to 0, you get this. Okay, and he could produce some more solutions. He found three cases, namely the A, B, C, D. He found out by actually this is not the complete solutions. They are the A, B, C, D. For this A, B, C, D, he found that he gives examples. I write this. I follow his symbols S7n, K from 0 to n and choose k square, n plus choose k, 2k choose n, and something as 10n, I'll write what the 7 and 10 means, and these are the numbers correspond to A, B, C, D, and this numbers, and choose k to the power 4, and he got another one for this particular A, B, C, D, 14, 6, minus 1, 92, 12, this particular A, B, C, D. He got another sequence, so the sequence is bit 2k choose k, 2n minus k, n minus k, times something looks like the similar 3k minus 1, n plus 2n minus 3k n, and he used this, okay, this 7 and 10 and 8, they come from these modular forms. Basically, the modular forms and that correspond to the level of the modular forms. So he used this 7, 10, and 8. After some, I'll write the modular parameterizations, and he made a conjecture by numerical things. He conjectured that Cooper S7 and P is congruent to S7n modulo P cube for P bigger than 5, and S18 and P is congruent to S18 and modulo P square. And using the Coaster method and using some more combinatorial tools, we could able to prove this in more general setup, namely we prove Osborne that S7 and PR is congruent to S7 and PR minus 1 modulo P to the power 3R for P prime bigger than 5, and similarly this is true for S18 and PR minus 1 modulo P to the power 2R. This proving basically these observations made by Coopers. And why these numbers are interested, because you use these numbers to get the new series of 1 by pi square. You use this particular sequence of these numbers. That's why Cooper was interested, and they just come from recurrence relations. Okay, so in the remaining time, maybe I'll tell you how the modular forms come into the picture, and namely the Baker's modular proof. I may give a simple proof of his congruence to modular forms. Okay. Okay, so this I call modular parameterizations and congruences. Okay, so Baker's prove that the numbers ANs have modular parameterizations. What do I mean by that? So if you take these particular forms, f of z is equal to this eta 2z, eta 4z, eta 6z, eta 12z. That's the eta and its duplications by 2, 4, 6, 12. And you take this is a more with two forms in gamma 0, 24. And if you take these modular functions, Tz, namely this eta quotient 2z eta 6 12z by eta 6 4z eta 6 6z. This is modular functions of weight 0. Then Backus proved that this if you write this an, the generating functions 2n plus 1, then you get this f of z. Okay, the t is function of z all. Okay, so if you take this particular modular functions weight 0 and you take this a n t to a 2n plus 1, then you get this modular forms. So this I mean by modular parameterization of the Apery number. Okay, and the proofs he used is more involved proofs with these differential equations. Okay, and one can use this to prove the modular congruence. I wrote that a p minus 1 by 2 is congruent to pth Fourier coefficient of some modular forms. Okay, so let me write a theorem that actually kind of come from the Backus works. Also, it was later proved by Veril in 2010, a simpler version of this Backus 1980, I think 4 paper on this modular congruence. So let me write the theorem in which we can use this to prove this modular congruence. Namely, let gamma be a congruence subgroup of level n. Let Tz be a modular functions. Let a modular function of weight 0 weight 0 for gamma. Let Fz be a modular forms, be a modular form of weight k for gamma, and I'm assuming let Lz be a modular form of weight k plus 2 for gamma, okay, which is an eigenform, Lz, which is an eigenform, or basically it says that eigenform for all the equators, or it is basically the Euler product expansion for these Fourier coefficients. And suppose that, okay, f of z equal to something like b and t. When you expand this fz at t, like this power series expansion at t, and let L of z has this Fourier series expansions, and the an's are the Fourier coefficients, q is e 2 pi I z. And suppose that f of z q dt by dq t is, we write this in terms of linear combinations of duplication of this modular form L, and for some this gamma d are some integers from integer combination of this duplication of the L Hecke eigenform. That's what I'm assuming. Okay, then yeah, then for prime p, for primes p, the donor divides n and m. Okay, the m is the numbers are coming from here, and integers MR in, okay, we have this, the 3-term congruence modulo p power r. So if I have this term is clear, so this is basically we are looking the generating function of t, bn's. Bn's is a sequence of integers like Apery numbers, and we are writing this. We are taking these as modular functions, and we show that generating functions is a modular forms. That's what I assume here. And if I write this particular, okay, one can show that fz times this is a modular form of weight k plus 2. Yeah, this is a modular form. Left hand side is a modular form weight k plus 2, which I can write as a linear combination of the Hecke eigenforms. If this is the condition given, then one can show that the numbers bn's satisfy these 3 terms congruence modulo p power r, and here the AP is the pth Fourier coefficient of the Hecke eigenform. Okay, so basically one uses this L series and this expansion to prove this. This is a little bit periodic, and one can prove this. And this was basically appears in the Baker's paper in 1984 and proved in a nice way by Verrill. And if you use this theorem, then okay, then the modular congruence of Baker's, namely, we know that this is the one we are taking, an t2n plus 1 equal to f of z. F of z is this particular example of forms with this particular choice. Then, okay, so I'm writing this f of z coming back to Baker's, this Apery numbers an's. So if you f of z is an t2n plus 1, and I can write this to be just change a variable an minus 1 by 2 tn and so on. And we see that f of z q dt by dq t is looks like lz minus 9 times L of 3z. So then one can use this recurrence relation for an's. Okay, namely, if you put this is true for this particular an, but an is here bn minus 1 by 2. So I need to be careful here. So that's why p minus 1 by 2 is coming in the Baker's relations. So then this congruence, what I wrote earlier, this is true for an's. If you took this, okay, your bm equal to here am minus 1 by 2. This is the original Baker's number, and that's what it comes to picture. And you prove that a p, if you take AP modulo p, if you take m to be 1, r to be 1, this term is no more there. So you get this term is 1. So you get b AP minus 1 by 2 is congruent to AP modulo p. If you take m equal to 1, r equal to 1, you get this particular congruence. And there are more congruence that one can gain from here. Similarly, a congruence of the form p square minus 1 by 2 is congruent to AP mod AP minus 1 by 2 modulo p square. One can give more general congruence out of this general theorem of Verrill. Okay. Yeah, so I want to make some remark here. So these two-term supercongruence, what I told earlier, two-term supercongruence, namely congruence of the type UMPR is congruent to UMPR minus 1 modulo P to the power KR, whatever I wrote earlier. So the basic way of proving is that what you do, you write UMPR, that's a sum K from 0 to something. So we split into two parts, the K with P divides K and sums K, P dot not divides K, the prime we are looking for. And then try to prove that this P, the terms which are divisible by P, they are congruent to U MPR minus 1 modulo P to the power the projected value of K, and the terms which are not divisible by K. So I have to prove that this is true modulo P power KR. So this is how this Koster method works. So which are divisible by K reduced to MPR minus 1 coefficients, and which are not divisible by K, that's come back to 0. But sometimes what happens that while proving this term, so there are okay, if you do the reduction modulo P, sometime if they are term wise they are related, then easy to prove. Okay, it so happens that the individual terms are not congruent to 0 modulo P, but the sum is 0 modulo P. So that case one has to be more careful and do some more work. So this is the way general Koster method works. Okay, and there are on the modular parameterizations, we wrote for there's number for ANs. So the question is that whether all the Apery-like numbers, namely numbers which are coming the way Apery numbers is arising from the recurrence relations, have always modular parameterizations. Can you get some modular function T such that the generating functions is a modular forms? And the question is, what should be the weight of the forms and how they are related to the sequence? This is the general conjectures of Jagiers. There is no general way of studying this kind of modular parameterizations. Okay, and similarly, we look for the congruence. They are related to the pth Fourier coefficients of these kind of things, like the way one proof for the Bayes number. So there is no general way of looking this kind of all the sequence. Okay, and but there is another way that was studied by Chan, Cooper, Sika. So given a sequence, we are looking for a modular functions whose generating function is modular form. But they study the reverse way. You take a modular form, you take a modular functions. So we write the power series expansion of f of z and find the ANs. Okay. So we start with the modular parameterization, look for the combinatorial numbers. Now, what kind of properties studies by what kind of properties are satisfied by these ANs? Okay, so they have studies of the reverse process of these modular parameterizations. And there is another type of supercongruence that comes from Ramanujan series of 1 by pi. Series of 1 by pi or pi to the power a. So let me, okay, yeah. So let me write down this one particular series of Ramanujan. So basically the series looks like j from 0 to infinity minus half j cube for j plus 1 is equal to 2 by pi. Okay, so minus half j means you have to write the rising factorial and write in terms of that. And there is a periodic version of this particular congruence. Namely, if you take j from 0 to p minus 1 by 2 minus half jq 4j plus 1 is congruent to, is stop at p minus 1 by 2. That is congruent to the minus 1 by 2, the Legendre symbol mod times p mod p cube. So we are stopping at somewhere at the finite field level. You are asking the question, what is the highest power of p? Okay. So this is the infinite. This is the version of Ramanujan. We are putting somewhere else, stopping at p minus 1 by 2, and asking that what is the thing on the right hand side, and what is the exponent one can prove for this congruence. Okay. This is called Ramanujan type supercongruence. Okay. So one can ask question, whatever Ramanujan series appears on the things, what is the corresponding supercongruence in the finite field level? So there are works of Julian and Morsons about this, but there are no general phenomena of this kind of things. Okay, maybe I'll stop here.